Okay, so let's review some of the material we covered last week. So we begin with two discrete random variables, and in this situation, we can define conditional probability of a random value x given this event, because y equal to sigma y is an event. We define in this way. So this is quite straightforward to give this definition. And of course, the denominator should be non-zero. So we should, given the condition that this event has positive probability. And with conditional probability, we can have conditional expectation. Because for discrete random variable, the conditional expectation is quite easy to define in this way. And of course, that this conditional expectation is a value, it's a real number. And so and it is given provided that the probability of capital Y equal to little y is positive. Okay? And of course that the sum, when we write the sum over x, we know, we understand that this sum is a countable sum. Because that the x, random variable x is a discrete random variable. And so now we are able to give a theorem to describe that if the random variable x has a finite expectation, then the conditional expectation we defined above exists, and it also has a finite value, provided that this condition is true. And because that because this is true for all the y, and because when we sum over all these probabilities, we have the probability 1. So we will say that this fact is true for almost all the y with respect to the distribution of y. Because that when we talk about the distribution of a discrete random value, actually we talk about the probability mass function. Okay, so actually probability mass function Py actually is defined by. Okay, so this is the for all y. Okay, and you can see that except for countably many y, that this value is 0. This value is 0, and this we know this is the called probability mass function. So okay, so this we know that from elementary probability table, and so that we have conditional expectation, and which is finite for almost all the y. If random variable x is a finite expectation. Okay. All right. So so now we establish a mapping, and this mapping is from the set of a real number to the set of real number, and the mapping actually specifies conditional expectation. So that, and as we know that we define conditional expectation only for all the y such that this event has positive probabilities. So that we have an arbitration to assign value for those y such that this condition the probability that capital Y equal to little y is equal to 0. And for example, here we will assign for example, we will assign the condition expectation. This value could be the expectation of X itself. Okay, when this condition is true. And some also I mentioned last week that someone just assigned 0. Okay, just 0 to this notation when this is true. Anyway, so the H function is as a function, the set of all real number is a constant function almost everywhere, because it's set for countably many y such that this probability is positive, because we have only counted many such points. So the H function is constant almost everywhere. Okay? Almost everywhere. And so you can see that the H function is for real measurable. Any questions? Yeah. All right. So now we define a random variable as a function of y. All right. So it's actually a composition of random variable y with h. Okay. So and so that sorry. Okay, and because y is discrete, so h of y is also a discrete random variable. So this is the this random variable what we call a version of condition expectation of a given y. So here given a random variable, not like here. In the original definition, the condition expectation is given an event here, right? It's an event, and so that okay. So the notation is quite different, right? And in this way, we focus on here, so that so when we look at the condition expectation like this one, we have to think about that it is actually y. It's a function of y. It's a function of y. And it contains, this random variable contains all the information about the condition expectation. Okay. And here we call it a version because we have other versions, actually many different versions of the condition expectations. Right? So the reason is that we will have different ways of assigning value for all y with 0 to 3 here. And of course that if we have two versions of the condition expectation of x given y, then these two versions must be equal with probability 1. The reason probability y is because that that for all so that if this probability is positive, then the value. So let's say. Okay, maybe I will show you. So let give you the event that is y equal to x on y. Okay. Right. So we want to show that this event has to be 1. Okay, so this event occurs. So now, when omega, I want to show you that if the union such that claim, maybe I would say claim the union of such as y is contained in P. Right? And actually it's a disjoint union. So I just take the union of all atomic events such that when we say it's an atomic event, we say that this probability is greater than 0 because it's in a range with positive probability. Okay, so the proof. To prove that a set is a subset of another set is to prove that whenever an outcome is in the union, okay, this implies that omega is in the, okay, for some y such that the degree of, okay. So this is the set, right? So the outcome is in the union, conjugate union of these events. Economy of omega is contained in some such event for some y, such as this is true. So that means that the h y omega, okay, because we know this is equal to expectation of x, y equal to, okay. Maybe I write one more thing. It's only y omega y for some y such that probability. Okay. So now I give implications, and then alright, so this implies that by definition of a version of O So no matter which version we use, whenever this is true, then the value, then the value, okay, is equal to the condition expectation. So that implies that H prime so they have the same value. So this implies that and so starting from here, that the outcome is in the union of this event. It implies that the outcome is in this event. So we show that this one contains B. Any questions?
为什么H bar y 会等于 expectation of x given y?
Here?
Sorry. The first part.
This part?
Upper part. H bar y. Yes.
Oh, it is the definition of composition of functions.
But in here, we didn't define what is H bar.
H prime is another version of the conditional expectation.
Is there another method that also maps to?
Yeah, it's another function, another H prime. Well, if we have two versions of condition expectation, these two versions must have the same value. So I have to go back. Right. I have to erase this part. Oh, yeah. All right. Let's see. Fine, right? So I can erase this. Right. Suppose this is one version. Okay. We define a version like this one, the function, okay, because it's a function from R to R. It's a real value function defined on the set of all real numbers. Okay. So for all y, in R, that the function value is equal to this condition expectation. to define for as conditional. Because we define that if this probability is positive. But if the probability is 0, we don't have any because when we look at the traditional definition of conditional expectation, it is undefined, right? So we have to assign it, right? So I decided to assign the expectation because usually we assume that X has finite expectation. Under this condition, we prove a theorem that then it's finite, right? And it exists. The other version, H from Y, and 0. Of course, these two will be the same if the expectation is 0. Yeah. Or you can, if you want, you can take 1. It can be assigned arbitrarily. Or you can assign to be y if you like. It's a continuous function, except the y is such that this probability is positive. So h from our h is a continuous function, except counted many points. So that's why it's for real measurable. So you can assign the value arbitrarily as you like. But the common practice is to assign this value. So you can use, for example, y squared if you like. If you like. So that let me just take this is 0. So h and h prime basically they are different functions, right? They are different functions. So we have two versions. So if so in general, h not equal to h prime. In general, they are different. But we call hy and h prime different versions of this notion. This notion means that conditional expectation of a given y. Because we want to define a function of y. We want to define a function, okay, to contain all the information about the traditional conditional expectation. Okay. So we find there are many, actually infinitely many candidates for this notion. So we said that there are different versions. And what I just proved is that for any two different versions, they are equal with probability. Means that in terms of probabilistically, these two random values are the same. Whenever we call two random values are equal with probability 1, basically they have the same distribution. They have the same distribution. Okay, and so we regard them as the same. Not the same. I mean, they are equivalent random variables. But they are probabilistic behavior will be the same because they have the same probability distribution function. Okay, so up to this point, are you okay? For this part. All right, so what I have done is that, 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 so what I have done start from here that for any outcome in this union, then we prove that this outcome is in this event. In this event. So that saying that this set is a subset of this set. Okay? And because this is the bigger set and this is the smaller set, so can I erase this one? Now since we have probability as we said, probability of any event will be upper bounded by 1, right? And what is this? Because it's a disjoint union, so this is become to summation. Okay? By the counteractivity of the real major. And because if you sum over all y such that it's positive, so this is equal to 1. Right? So 1 is less than equal to this one, and this is upper bounded by 1. So the only way to see is this implies that probability equal to 1. So this event occurs with probability. This is a very common technique that to show something, to show an event that occurs with probability 1, you find a subset, and this subset occurs with probability 1. Because to show it occurs with probability 1, sometimes it's difficult. Sometimes it's difficult. So instead of that, we find a subset and show this subset occurs with probability 1. And we have that. So that is this is a very usual practice. Alright? Any questions? So you can see different versions of the condition expectation of x given y are equal to each other with probability 1. So they will have the same distribution. Maybe I have to give you a lemma. Maybe I have to be careful. Lemma. And x. So suppose we have two random variables. If x and y are equal with probability 1, then the probability distribution function, or sometimes people say that cumulative distribution function of x equal to the cumulative distribution function. Okay, so we have this property when they are equals. Okay, and the proof, like this one. Well, consider the event. Oh, sorry, we have to use the same. We have to use the same value. Okay. This is an event, right? And this event set a total event, right? Okay. And the intersect the total event is the joint union of x equal to y and x not equal to y, right? This is a complement of this event. So this is equal to okay. Now, because x equal to y, right? Under this one, so we can replace that y. And okay. So all the identity and just use logic to show you. Now, probability of, well, so you can see this is the joint union. So this probability is equal to the sum of this probability and this probability, right? So you have okay? Up to here, everything is perfect, right? Now, back is a subset of, right? Because it's to put more restriction, so this is smaller. And similarly, okay? So now, things. So we have the probability of is less than equal to probability. Is that okay? And right? And what is this probability? What is this? Can you give me an answer? 0, yeah. probability is 0. And the low bound is 0, right? Because probability always non-negative. So it shows you that this is 0. Right? Again, it's difficult to prove that this probability is 0 directly. So I use bounding, right? Again, I use this practice, okay? Because it's much more easier to use the bound. Okay, so this is 0, but this probability is less than this probability. So what I found is that probability of x is less than or equal to 0. Is that correct? Right? Similarly, I can do it again for here. I can do it again, right? If you start with y less than or equal to x, you will end up with the same inequality. With this inequality, so okay, I give you a very rigorous proof, step by step, right? In elementary step by step. And I show you the technique to prove two quantity to be equal. A common practice is to show one is less than another one, and then reverse it. Okay, so they must be equal. Okay? All right. Remark. The converse of the previous lemma is also true. Means that if I have two random variables with the same distribution function, then these two random variables must be equal. Okay, and so the comments is also true. And you may think about how to prove it. Okay, so so now we know we have many different versions of conditional explication of x given y. Okay, and any two different versions will be equal with probability 1, so that they will have the same probability distribution function. All right, so we okay. So up here we have any two different versions. They must be equal to probability 1. Okay. So this is a common way to show you. When you use H as a version of the condition expectation, then we write this. The value when we observe an outcome, then the value of the condition expectation of x given y, by definition, it is equal to this one. Okay, and of course you may argue that y is equal. Actually, it's equal to square root v1. Okay, but in this case we set it as by setting the equality here. And so it's this value. Okay? So you have to, first of all, you because it's a function of y, right? So first of all, you have to find the measurement outcome by y. Right? So you have a value little, this is little y, right? Little y here. And then with little y, you know how to compute this condition. Now, it's quite often we have to consider condition expectation like this one. We consider condition expectation of x given an event, right, in the information system associated with random variable y. Right? So P is a Fourier set, and such that this event occurs with stochastic probability. Now, the indicator function of Fourier set is defined in this way. So, indicator function of a Fourier set is also Fourier measurable. So, it's quite easy to check it. Okay? So, the indicator the indicator function is a function from R to R. Okay, from R to R, and the value is equal either 1 or 0. Okay, so it's R to R. Alright, now, the condition expectation of x given this event, by definition, this is because we assume that this event occurs with stochastic probability. That's why we can put into the denominator. Right, and so this by definition is here. Okay, because this one, by definition, okay, this is by definition. And so to put here, okay. And now we do some manipulation that alright, well, we now decompose because this event is the disjoint union of and as before, when we so this is one, this is the disjoint union, okay, here, and we have an understanding that because y is discrete, so possible values are countable. So at most, this is a countable union. Okay, countable union. Because if y is not a possible value, then the event is an empty set. They are all empty set. Okay, so we have this one, and this is the joint union. So that the event becomes to joint union. Okay, return becomes to this joint union. That's why the probability becomes to the summation of this probability. So that's why we have sum here. Okay, sum. So this is implies that region. So that's why we replace this probability by the sum. Sum. Okay, and now we introduce the indicator, so the sum can be over y, no restriction on b, right? On the Fourier set, right? Because when y is in b, this is y. Otherwise, when y is not in b, this is 0. So they are equal. And this is the joint. This is the joint probability mass function. Okay, so it comes to the expectation of this product. Okay, this is x here. This is 1by. So it's a function of y. And provided that this expectation exists. So my purpose is to represent a traditional conditional expectation of x given an event which occurred. This event occurred with positive probability into an expression without condition. That is a miracle, right? You can say that. This is the significant part that we are able to express conditional expectation to something without condition. But we find the interaction between x and y here. It becomes to a product. We are considering the expectation of a product of x and y, a function of y. A function of y. And this function depends on the Fourier set we specify in the given condition. Okay? And don't forget this is a normalization. Normalization factor divided by this. And this is very important. All right, this is very important. So, please examine it, and we will continue to explore conditional expectation on Friday. Because conditional expectation is so important. In the remaining semester, I will use conditional expectation all the way. All right, and we will have a makeup class. On October 5th, Saturday. All right, and from 8 o'clock to no, 9. The reason is because we have a long double 10 weekend, right? And in the calendar, in the university calendar, that teacher can decide whether or not to have a makeup class. My decision is yes, we will have a makeup class. All right. So the makeup class will be this Saturday in the morning from 8 o'clock to 9. Okay, so don't forget to come. Alright, and I will send you an email message. Alright, so see you on Friday.